flow. So this is the design and manufacturing flow for a given integrated circuit that you have here. So basically, you have two big steps: the design and the manufacturing. So the design, you do the model, and then once you have the model of your electronic component, you go for the production. So basically, you have your piece of silicon that will be finally put into the package and then shipped out to the final application. So hardware faults can appear here during the manufacturing process. And basically, for sake of simplicity, an hardware fault is simply a physical defect. So yeah, it is an imperfection in the product device. Here, for example, I hope you can see that there is a missing connection between this element and that element, right? Like it should be here and here. So this clearly means that this device cannot work properly as expected. And this situation is absolutely random. You cannot forecast where this problem can appear. Clearly, this is simply one type of problem. You can have many other. And this is just one device, one transistor. You, I think, know that nowadays we talk about trillions of transistors. So clearly the complexity of spotting up these specific defects is very, very low. So the probability to detect this. How the companies, how industry deal with these kind of problems, they simply do the test. So they check every manufactured device that properly works. If yes, then the device will be used in the field. Otherwise, you simply throw away. Now, the problem is that even if you test once you manufactured your device and you don't detect any potential problem, and so you will use it in your final application, the problem is that in the field, you can always have potential problems. First of all the electronic components are subject to the aging phenomena. And because of the aging, basically you have degradation. Your performances degrade. And at a certain moment, simply some components does not work anymore. Right. Then you can have what is called test escape. Basically, you can have a very, very small defect. In my previous example here, you have a complete missing elements, but you may have a very thin connection. A thin connection means that it could work under some condition or it cannot work under other conditions. So it depends on the way you test. So this is called a weak defect. So you may declare your device fault-free, but at the end of the story, because of this weak defect that you were not able to detect, it may be basically sensitized later on in the field, so during your application use. And the last category of problems is the interaction with harsh environments. The classical example in our community is, for example, the impact of radiation coming from cosmic rays. So even if the magnetic field of the Earth basically protect us, some particles still can enter and we can still have problems at ground level. And those perturbations can really impact the behavior of electronic components. So those are the problems. And the key point is, okay, we have those problems, but how they will behave with respect to my system and with respect to the application running in my system. So this is just a scheme in order to represent our computing system. So basically you have a certain amount of hardware layers and then software layers. And as we presented so far, fault impacts the technology, so the electronic devices at this level. And then this impact means that there is a deviation of one or more component with respect to the normal behavior. And this deviation can be basically propagated through the other abstraction layer. And it can become an error. For example, one variable in your software basically change its value because of the fault. And depending on the software layer, the errors can be propagated to reach the output of our application. At this point, you can have a failure. For example, your training job that is not completed, or for example, the pedestrians that are not detected anymore by your application. Now, this process of understanding what happened on your computing system when a fault impacted the technology is called the dependability evaluation. And for us, clearly is related to the evaluation of AI systems. So dependability is what? Dependability is basically the quality of a computing system to be trustworthy and reliable. So clearly is what we need to satisfy our definition, right? So how we can proceed with the dependability evaluation? Basically, the common approaches used by researchers, but also by companies, are known as fault injection techniques. So fault injection, you can see in this scheme, is simply a way in order to basically inject or introduce a fault into the target system. The target system is supposed to execute a given workload. The workload is basically the operations that have to be executed by the system. So basically is the software, the code, and the A is activation. So A means the data that have to be manipulated by the workload. So we can consider this as the AI model that is executed on the system, and A basically is the set of inputs that the AI model has to process to perform a given inference. Because of the fault, the results can be different from the expected ones. So we have here this collector, so we have this readout, so we have the information of what happened to the output because of the injection of the fault, and then we have to analyze those readouts in order to determine how many of these faults basically really impacted the execution of our AI system. Now, this is a very simple definition. The process itself is very, very simple, but the problem of this process is the scalability. Just to make an example, in this book, basically, there was a comparison of different ways of running fault injections. So we can basically execute fault injection at software level, at the architecture of a given microprocessor or GPU or whatever, or we can basically go down to a more detailed hardware model that is called the RTL, Register Transfer Level. So basically is a very low-level description of the architecture of a given processor. And you can see here that if we consider the simulation time, without injecting faults, we basically go through 25 milliseconds of the software execution, up to 20 hours to simulate the complete model of our computing system. And just to give you the complexity, we talk about a microprocessor having 4 kilobit of a register file, so it's a very small microprocessor. And basically, in terms of software, we executed here. So the workload was one benchmark from the IPC suite. Basically, in terms of instruction, we talk about 50 million of assembly instruction. So if we compare this with the complexity of a given GPU and a given AI model, we are very far. And if you consider the number of time we have to inject faults, etc., you can see here that still, if we consider the lowest level, we can go up to 40 years of evaluation time. So clearly there is a cost, and here we inject 16K samples, 60K faults in our fault injection campaign. Those numbers came from a specific, there is an evaluation. So basically there are formulas that allow you to sample a significant statistical set of faults. So basically, this means that if you inject these 16K faults, you have something that is good enough in terms of dependability evaluation. 40 years for the lowest level, 7 means for the software, but you may have differences. Why we should go there if we can simply do at software level? And this is one point. And I will show you now what is the point. So if we look about fault injection specifically for AI, you have some, let's say, academia work. So this is one of the work we did in the past. So this was in 2019. But there are also some more, let's say, industrial, let's say, tool. One is PyTorchFi, based on PyTorch environment. The other is TensorFi. And those two are very well known and used for both academia and industry. So the common point of these fault injectors is that they can perturbate basically the structure or the parameters of a given AI model. So they limit themselves to the software implementation of a given AI model. And this is a problem because if you look here, basically you have so this is a super simple example. This is ALENet 5, but the point is that I use this because you can see the histogram showing the failure rate when you inject in the memory. So basically, when you use the classical way of modifying the parameters of your AI model versus injecting into the registers of the processor running the model. So you can see that you have a huge difference. So this means that you cannot relate leverage only on a pure software level fault injection, because otherwise you can have a very wrong figure of the dependability of your system. So this is to once again show the importance of the hardware. Now, why we have this discrepancy? Some examples. So first of all, let me introduce briefly a given dedicated hardware for AI. That is basically a systolic array, but why we are at the systolic array? First of all, one common point is that the most executed computational kernel in AI workloads is matrix-to-matrix multiplication. So there are works basically showing that almost 99% is matrix-to-matrix multiplication. Matrix-to-matrix multiplication is complex if you run on a CPU, because basically you have a huge complexity and power 3, assuming that you have the same dimension of the matrix, but let's say this is complex. So systolic array allows you to easily implement the matrix-to-matrix multiplication. Basically what you have is an array of processing elements. Each green box is a processing element that can do the computation. You have on the rows the elements of your matrix A, and on the columns the elements of your matrix B. And basically those elements are shifted into the array. And every time you have a shift, you do a computation and you accumulate the results. So here, at the end of the story, you have your resulting matrix. And if you count the number of cycles you need, you have something that is close to the linearity. So you reduce the complexity of your matrix-to-matrix multiplication. Okay? I did this example not to introduce the systolic array itself, but just to make an example of differences between injecting in the memory and injecting in the hardware. So if we inject a fault in a memory, so we can modify, for example, the parameter in matrix B. It was 3, now is 4. If we do the multiplication, we have this wrong column with these wrong values. On the other hand, we can inject into this first processing element, and by doing this, we impact all the elements flowing through this first column. And if you compare, you still have the first column that is wrong, but the values are quite different. And basically, you can have, depending on those values, you can have difference at the end of the story in terms of application outcome. Then you can have other problems. You can have a fault here that impacts not only a column, but can impact also this row. So this is something that you cannot have in your matrix that results from the multiplication from a wrong value in the memory. So this is an example that somehow should help in understanding why we can have this difference in terms of faults injected into the hardware. So one point is that depending on the hardware itself, specifically for the systolic array, because I use systolic array because we did some works in this, but the point is that systolic array can be designed to have different shapes. 1, 2, and 3 are some example. Basically, it depends on the way you arrange the operations. And if you do fault injection on these different basically shapes of your systolic array, you can have a different number of problems. Here you have basically what happens in terms of critical. So really your model is not able to classify correctly the input image, or it is masked, no difference at all, or you have a difference, but you are still able to correctly classify the image. So the interesting point is that in all the 3 cases, the percentage of critical is very, very small compared to the other 2 cases. But if you look, you have a specific data path, this one, a specific shape that is really showing a very, very low or negligible, I would say, percentage of critical faults compared to the other. So if I have to choose in terms of dependability, I will use this one and not this or that, because by design, let's say this is more reliable, more robust. Now, the point is that we now know that we have to deal with the hardware, so we have to go in this very time-consuming window in terms of fault injection experiments. And one of the research questions that is very, let's say, popular today is how we can reduce, sorry, try to minimize this window. How we can reduce the fault injection time. And basically, you have 2 ways. One is reduce the percentage of faults to inject, because it means that you have to run less campaigns. And the second one is to reduce the amount of workload, because I remember that when you inject 1 fault and you are analyzing your AI model, and if you have 10,000 input images, you have to simulate all the 10,000 input stimuli. That is very, very costly, once again. So in terms of reducing the amount of faults to inject, there are techniques. I will not describe the technique. I simply, let's say, try to provide you the main message. So what is this table? First of all, we target here 2 CNN models, ResNet and MobileNet. The dataset is CIFAR10, so it's for image classification. What we use in terms of fault injection tool was PyTorch FI, customized. And what we injected was basically faults impacting the weights of the CNN, right? So here the goal is not to compare this way of injecting faults with an hardware-aware fault injector. It's simply to determine how we can reduce the amount of faults. So since we know that we target the CNN weights, basically all the weight can be a target, a potential fault. And basically, since each weight is encoded in 32 bits, you have to multiply 32 by the number of weights, and you have your overall amount of possible faults. This is the exhaustive fault injection. So you should inject all these faults to be, let's say, sure that you evaluate all the possibilities. What you can do, and those are the techniques available in the literature, you can do statistical fault injection. So you can basically extract a given number of random samples from this population. And you have 2 ways to do. The classical way was to use what is called data unaware approach. So here you have your results. The other way is using data aware approach. And you can see that by using this one, you can really reduce a lot the amount of faults that you have to inject. So what is the difference? Basically, here you consider that all these faults, basically all the faults in your fault universe, have the same probability to impact the execution. While with the data aware, you have different probabilities. And just to make an example, very, very simple. If you consider your floating point that is used to represent a weight, if you modify one bit in the mantissa, the modification is very, very small. But if you inject one fault in the exponent, you can have a very big variation. So it is most of the time useless to inject faults in the LSBs of a floating point variable. What you should do is inject faults in the exponent, because those have the probabilities that is higher in order to modify the behavior of your application. Another way to reduce the fault injection time is to reduce the amount of workload. So here is what happened when I have to evaluate CFAR 10. So I have 10,000 images. And if I apply randomly, you see that the amount of critical faults slightly increase, and I have to apply all the 10K images to reach the overall amount of faults. But I can try to use some metrics to order the images. That can be some Euclidean or correlation metrics, cross entropy loss, Gini or probability vector, etc. So all of these are under evaluation. This is just an example in which we use a correlation coefficient. And basically, thanks to this, you can see that the difference now that in order to reach your plateau, you don't have to apply all the 10K images, but you simply have to apply almost 1K. So it means that there is the potential to significantly reduce your amount of images during the fault injection. That once again means that you reduce your fault injection overall time. Then what you do when you know what are the problems of your hardware in terms of dependability. So you want to do is add countermeasures. So basically make an AI system robust. So make it able to function even if you have a fault. So what you have to do, you have to evaluate what could go wrong, so the potential risk, in order to basically design and implement a proper protection mechanism. So you can see here that this protection mechanism is not really adequate with respect to this. The problem is that bigger is the safety mechanism, higher is the cost. So basically you increase the area, you increase the power consumption, you can increase the time, etc. And you have here some examples. So error correction codes in the memory, you can triplicate your system or part of your system and then boot, etc. So just a few examples, because the time is running a little bit fast, of fault tolerance or correction mechanism. So the first one is what is called graceful degradation. And again, those fault tolerance mechanisms are dedicated to AI systems. So what you have here is again a systolic array. So each block M is a processing element, and the red ones are processing elements that are faulty. So you know that those elements are faulty because basically you can somehow test each of these elements. So you can determine the quality of each element. And for the red ones, for the faulty ones, what you can do is simply add this multiplexer, these elements that allow you to either use the unit or skip the unit. So for the output of this block will go directly to that one. So this means that you don't use any more faulty processing elements. That at the end of the story is like setting at zero the contribution of this element. And setting at zero the contribution of a given element is nothing else than performing a kind of pruning in your AI model. And you all know that pruning is a very efficient way to reduce the complexity of the network, and the AI models are robust versus pruning. You can see here, for example, that you have depending on the increase of faulty MAC, the degradation of the accuracy of your application. And this is the blue curve. So first of all, you can safely, let's say, tolerate up to, I would say, 15% of faulty MAC. But what you can do more is basically, once you know that there are some of these faulty, you have the failure bitmap, you can basically do a retraining step in order to recover. And this is illustrated here in the red curve, in which basically you can tolerate up to 50% almost without any impact on the accuracy. Then if you zoom, you have a little bit of impact, right? But you still are much better than the blue curve. So this is the zoom of this behavior. A second one is to apply the error correction code. So basically, if you have here your metric, so you have 8 bits per each weight. So in this example, what you can do is you can use, for example, the LSB, so this column, as a parity bit. And if you detect an error thanks to the parity bit, you can correct the error by simply setting at 0 the complete weight. So it's not really an error correction code, because parity bit is not, you can detect one fault, but you cannot correct. But if you do the correction in this way, you actually do a correction and once again correspond to do a pruning. And once again, you have a certain resilience of your model with respect to the pruning. So this chart here is related to the results applied to MobileNet, in which you have different types of data. You have two nets, mobile and SqueezeNet. Floating point 32, brain float 16, and integer 8. And basically the different curves depend on how deep you apply these techniques. So every weight is the dashed curves that is always the best, except for this specific case. So this is very interesting because this is the only case in which basically if you do not apply the opportunistic this technique, basically you have the better resilience. And this is really specific to this way of representing the data. Because here you have the same model, different data, you have completely different results. So this means that I put this slide not to show that there is a problem, but to show that it is not only necessary to target the hardware or the software. You really need to target the system in an holistic way, because here your techniques have to take into account the model itself, the hardware, but also the way you represent the data. The last technique that I will present to you, and then I will conclude the presentation, is what is called timing redundancy. Basically, the idea here is to, let's say, somehow cut your model. So here we add something between the first and the second layer of a given AI model. And basically, what we do is we compute on the fly a given metric. We check if the metric is below an acceptable threshold. If yes, we consider that the execution is okay and we go ahead. If we have if the metric is below an acceptable threshold, there is a kind of warning. So something is not really going well. So what we do is we recompute the first layer, we redo the metric, and if we talk about a transient fault, so by doing the computation we can recover, so we can go in this way. Otherwise, we really have a warning signal, because either we have something that is permanent, or we have other kind of problems that basically lead us to have a behavior that is outside the expectation. What are those metrics? Well, for the moment, we simply consider max, mean, and the sum of the output feature map of a given layer. And the tricky point is that what we should do is we should profile this, the metric, in this case is the max. So this is the absolute value of the output feature map. And this is the histogram of the how many times we get this value, etc. when you apply the complete data set. So this is not the fault injection, simply the profile. And then we have to set a threshold, for example, here. And when we set a threshold, we have to take care of false positive, true positive, false negative, and true negative. Because clearly, we want to maximize the true positive, and we want to minimize the false negative, etc. So this is, once again, not a trivial design problem, because we have a lot of parameters. So the main concept here is the following. So the goal is to try to detect as soon as possible a potential problem in order to avoid to really go and compute all the layers to reach the output, but recompute only the suspect layer and then recover. And this works very well if you are in a, let's say, very deep network. So if you have a lot of layers, and it really makes sense to really stop if needed at the very beginning and recompute at the very beginning, instead of waiting for reaching the final output. So this concludes, let's say, my presentation. And just to make some general conclusions. So the main message was that hardware plays a crucial role concerning the correct execution of a given AI model. Hardware itself, and most importantly, hardware faults. The origin of the hardware faults are very different, so you have to take care of this in your design process, but also, let's say, to put in place countermeasures during the in-field application. The problem is that the way to evaluate how those faults will impact your system is very costly. So what you have to do is you need to, on one side, speed up, and on the other side, to be as precise as possible, because you have to target the hardware. You need to develop design space explorations, because you have to basically design efficient but also adaptable countermeasures, because faults can vary during the in-field. Simply think about the aging effects. And then clearly you can imagine to do training. There are techniques about fault-aware training, but these training techniques, in order to make the network more robust versus faults, are efficient, but again, they need long fault injection campaigns. So we come back to the beginning, how we can improve the fault injection, right? So this is the big message of the presentation. And yeah, so this is the name of the project. So it's Adaptive Architects for Embedded Artificial Intelligence. So the keyword is really the adaptation, because we have to be able to adapt on different, let's say, conditions. And one of these is the external behavior and the hardware that can, as you see in the presentation, really impact the behavior of your AI model. Thanks for your attention, and if you have questions, I'm happy to answer.
Yes, thank you, Alberto. Very interesting. And you leave this slide. Can you leave it for a few seconds more? Because in fact, I forgot to launch the recording at the very beginning, so I missed the introductory slide. So it's good that you have it back here.
Okay.
I think that there's everything on this slide that we need to know about the presentation. Maybe just the title, but we have the title as well. It's no problem. So okay. I see one hand raised by Christophe. So Christophe, you can go first.
Yes, Christophe Guettier. So I'm expert in Safran Electronics and Defense, and also Safran Group, expert emeritus. So thank you for the presentation. So I've been studying the systolic architecture for a long time ago. So those are old types of architectures, and also we are working in Safran in the aeronautic domain, and we are developing, onboard processing.
Hello,
Christophe, can you reactivate your microphone? I did something wrong, please.
Okay,
now it's good.
So I was saying, I've been studying systolic architecture on one hand. On the other hand, I've been involved in many dependability analysis from about 20 years, and especially for aircraft systems or military systems, where you have, as you mentioned, heavy particles that are very very nicely accelerated, and that hits the electronics and involve bit sweeping and things like this. Well, I was wondering, in fact, what you are saying is that there are new types of behavior that we didn't see maybe in classical architecture, dependable architecture for aeronautics, for instance, that may be characterized with this approach, because I don't see what's really new in this. You see, because we do already develop dependability analysis, and in terms of techniques, what is imposed to reach a certification level is really to provide proofs about the electronic that it will sustain that amount of attacks, or that amount of bad events or hazard in a given number of hours, things like this. So, but you need to come up with, so there are multiple approaches to build those proofs. And it's for me, it's very important that if we want to embed AI in future aeronautic and space systems, we would need to be able to provide real proof. Could be based on probability, but also sometimes it's based on pure logic, like temporal logics and other kind of thing. And we, in the past, already managed to deliver these types of proof, even in very complex systems, such as system of systems, because dependability analysis in system of systems is just fundamental. It's sometimes it's forgotten by even by people working in the aeronautic domain. But I think the approach is interesting, but we would need to cover more aspects of dependability analysis in order to provide really safety guarantee and achieve sometime eventually a certification process. So I haven't seen a lot of work on this, and I think it's quite interesting to tackle the problem on the specifics of neural network algorithms. But well, what is your feeling? So do we need to develop more techniques within the scope, or do we need to go in depth and study neural systems and specific architecture? I don't know that.
Yeah, okay. So thanks for the comment. And yeah, you are absolutely right. So the certification itself is another big problem that I completely not consider in the presentation. So the presentation also is not really, to me, was a little bit more like a tutorial. So I really didn't present super recent research-based techniques. But coming to your point, yeah, I don't think we really need to develop something completely new, in the sense that, for example, for all the fault injection techniques that I presented are something that exists from many years. So there is nothing new. There are techniques about, as you said, also based on formal proof, so model checking, assertions, etc.
Yeah.
This is still valid in my opinion. What is different is, let's say, the application itself, because neural network are on one side much more complex than the software that we used in the past. And on the other side, those neural networks in general also present a certain degree of intrinsic resiliency. This is why you can do pruning and other compression techniques. So what I mean is that if in the past, for example, any deviation you can observe from your software means that you have a potential fail, so you have to take care and you have to do fault injection, you have to do validate, etc., etc. From the neural networks, a single difference in one bit at the output could be simply nothing, because your network can still work properly. So I think this is the real challenge. So you have a more complex taxonomy of, let's say, faulty behaviors. Not all of them led to failures or critical situations. Some of them can be latent, and this increases the complexity of the analysis. So in this sense, you have the challenges.
Yes, I think you're right. I think that's what I understood from your presentation, is that the problems raised by faults could be hidden by the neural network because of this intrinsic property of resilience. And yeah, I think could be a real danger. So my question then is, so we agree on that. I think this is a good point. And so then my question is, can we build some failure detectors? Because one of the main questions for aeronautic systems is a classical, failure detector, fault detection, isolation, and recovery principle. And also to face these problems, we have computation monitoring architectures with a level of redundancy and consensus type of algorithms or distributed agreement. So that you can build these famous proofs. In this case, I think maybe those architecture would not be directly applicable because of this capability of the network to continue to function even if an error is injected. And so the idea would be, can we build some type of failure detectors that are taking in account the characteristics of neural network and the propagation of the information in the neural network in order to detect faulty behavior online? So that's the question.
Yeah, absolutely, yes. So, and the point is that just to make a very maybe stupid example, but you can easily triplicate, for example, your the complete systolic array, and then vote. But these are clearly as a cost that not all the applications can basically afford. So what you can do is, if you are able to do this dependability evaluation, you can understand what are really the critical components. You can only triplicate those specific elements. For example, some neurons, some layers, so you don't have to triplicate the complete system, but you can really do something focused on your application. This clearly means that somehow you do application-specific fault tolerance mechanism. So this is also another, let's say, problems, because if you change your AI model, you have to do the dependability evaluation. You may need to, let's say, design a new contour measure. So, but on the other hand, you can have something really efficient, and you don't have to spend a lot of overheads in terms of this. So the key point to me, at least what we are working on in the project, is really to be able to implement something that can be that can evolve, can adapt. And the example of the monitors that I presented before is something in this direction, because in terms of hardware, you have this monitor that always check the output of a given layer, but then those thresholds and the metrics that you have to compute can be programmed. So in this sense, it's something that can be adapted to a given AI model. Clearly, you have to do a profile, you have to do analysis before, but once you have this information, you can program your, let's say, detection monitor in order to basically trigger or not this warning signal, and then think about countermeasures, etc.
Yeah, thank you very much. Very interesting answer. So could you please, if you have some kind of literature...
No, I have to stop you.
Yeah, just if you can send some papers, if you have on this, that would be just great.
Going in contact, keep the contact with the two of you. I think it's very good that you have this interaction, but we need to move to the second speaker. I'm sorry about that, because I think it's, I know that when we talk about AI risks and about trustworthiness, etc., most of the time we forget that we are working on hardware and that also these faults. And when I look at AI index, published each year, there's almost nothing about hardware. When I look at what we do on the risk standards for AI with Sensenelec, we don't really talk about that. And I think that we can be sure that there will be hardware faults with the numbers of components, etc., that we have. So I think it's a good message that you gave, Alberto, and that we need to take care of that.